When driving down a rainy highway at night, you rely on a single piece of technology to keep you safe: headlights. Yet over the open ocean, you will see multi-million-dollar cargo ships pushing through the pitch-black water without a single forward beam to light their path. Why do these massive vessels navigate in such deep darkness? This animation shows a car traveling at highway speeds. A standard headlight projects a cone of illumination about 100 meters forward. Because friction brakes allow a stop well within that illuminated zone, 100 meters provides plenty of warning to avoid an obstacle. But a commercial cargo ship deals with a scale of momentum that overrides the safety logic used on land. Without tires and tarmac to provide friction, these vessels have no way to shed speed quickly. To bring hundreds of thousands of tons of steel to a complete halt, a fully loaded cargo vessel requires a mile or more of open water. If two of these ships approach each other head-on, their combined closing speed means navigators need at least 2 miles of clear visual warning just to take evasive action in time. The mass and momentum of marine vessels make short-range forward illumination a functional impossibility. 100 meters of warning provides no safety at all. To see an obstacle 2 miles away, we have to look at how a headlight functions. It is a concentrated source emitting photons. Those photons must travel forward, strike a target, and reflect all the way back to the observer. This diagram illustrates light propagation. As the beam leaves the source, intensity degrades quickly over distance, thinning the light before it reaches its target. When that beam hits a surface, most energy is scattered. The returning photons thin out even further, leaving almost nothing to reach the observer's eye by the end of the round trip. Scaling this two-way energy loss across a 2-mile stopping distance demands power levels that are practically unattainable. To successfully illuminate a dark object 2 miles away, a ship's forward beam would have to be incredibly intense. The resulting glare from this massive light would completely blind any other navigator on the water. Since relying on reflected light across vast ocean distances is an optical dead end, safe nighttime navigation requires a different strategy. Instead of trying to illuminate the path, the maritime industry uses direct transmission navigation lights. This diagram shows why this model is more efficient. Because the light source is mounted on the target vessel, the photons only make a one-way trip. This eliminates the massive energy loss of a reflection. This system turns a ship into an active broadcaster of standardized geometric data. The foundational layer of this data network relies on the dual white masthead lights displayed by power-driven vessels. International rules dictate a strict vertical arrangement. On this profile, the aft masthead light is always mounted higher than the forward one. This offset creates a parallax effect. If the lower white light appears right of the higher light, the vessel is moving right. A simple difference in mounting height converts two static lights into a continuous broadcast of a ship's trajectory. Moving down from the masts to the hull level adds a secondary layer of information, the colored side lights. By universal maritime convention, the port side is marked with a red light, and the starboard side is marked with a green light. These colors offer an immediate confirmation of aspect. Spotting a lone red light moving across the horizon means you are looking at a port-side crossing. Combining hull markers with masthead lights calculates precise vectors.
Watch as a vessel turns. The offset masthead lights close the gap, snapping into a vertical line. Seeing this vertical white line alongside the red and green markers confirms the vessel is heading directly toward you. These strict color and placement rules allow a navigator to determine an approaching vessel's heading in seconds without ever needing to see its hull. The engineering of these lights also covers the rear of the vessel, using a technique called optical baffling. Masthead and side lights are mechanically shielded. These baffles block photons from emitting toward the rear of the ship, creating a controlled blind spot. A single white stern light fills this void, mounted at the extreme back of the vessel. The stern light is bound by precise geometry. By international mandate, it must project an exact arc of visibility of 135 degrees. Splitting this arc dead astern means the light extends 67.5 degrees outward on either side of the vessel's centerline. In navigational terminology, an angle of 67.5 degrees from the stern is 22.5 degrees abaft the beam, or behind the widest point of the ship. Restricting light to these exact angular fractions divides the water into specific mathematical zones. This 135-degree optical geometry is the basis for the primary international legal framework, the Collision Regulations, or COLREGs. This geometry dictates right-of-way. If an approaching vessel is positioned inside that 135-degree arc where only the white stern light is visible, the law defines it as an overtaking vessel. Overtaking ships are required to steer clear. The legal transition occurs when the overtaking vessel alters course enough to cross that 22.5-degree boundary line. The optical change is instantaneous. The white stern light is immediately cut off by its physical baffle, and the colored sidelight comes into view. The edge of a light baffle serves as a hard border for maritime law, shifting legal obligations based on these unyielding optical thresholds. The open ocean is populated by different classes of traffic. Agile cargo vessels must navigate alongside ships engaged in specialized work. The COLREGs manage this diversity by establishing a hierarchy of right-of-way, prioritizing vessels that have the least ability to get out of their own way. To broadcast these limitations, ships hoist vertical stacks of all-round lights that override standard navigational markers. This diagram shows the configuration for a vessel not under command. It consists of a vertical stack of two solid red lights. This indicates a propulsion failure, forcing standard traffic to yield. For vessels restricted in their ability to maneuver, a red, white, and red sequence is displayed. This indicates complex operations, like launching aircraft that prevent easily altering course. Navigation lights form a modular language, allowing baseline vector data to be overwritten by legal modifiers. For a navigator standing on the bridge at night, parsing this data is a continuous discipline. Moving thousands of tons of steel through total darkness without forward illumination is counterintuitive, but a headlight is a limited tool. It only addresses visibility, which is insufficient for the stopping distances required at sea. Direct transmission arrays solve a more complex problem. In a single glance, they transmit exact vectors, specific headings, and legal authority. The maritime world replaced the limited utility of illumination with a system of encoded data, providing the specific information required to apply the rules of the road in total darkness.